Hello everyone. Today we continue talking about distribution systems and we want to introduce an algorithm for solving the shortest path problem. It is called Dijkstra's algorithm. If you remember from the previous class, we talked about shortest path problem, which is defined on a graph like this, and we want to find the minimum total length passed between specific pairs of nodes. So for example, in this graph, if you want to find the shortest path between A and D, just by inspection, you see that the shortest path is AD and its length is 7, because if you take any other path, it's going to be more than 7. So for example, if you go from A to C and then to D, it's 9 plus 3, which is more than 7. But the question is, if we have a node and we want to find the shortest path to all the other nodes in the network, how can we do that? Okay, yes, one way is enumeration, but it may work for this small network, but if you have a large graph, it's not going to be efficient. So we introduce the Dijkstra's algorithm to solve the shortest path problem. It is one of the algorithms that is based on the dynamic programming. And the idea is that if we put a label on each of the nodes at each stage of the dynamic programming that shows the shortest path to that node that we have found so far. Okay, so in the first stage, the shortest path from A to A is obviously 0, but for the other nodes, because we haven't done anything yet, we put the worst case, which is infinity. Okay, and we have two different tables. The first table take care of the labels and their updates, and the second table keep track of the paths from each node, from each of the nodes that we have. Okay, what's next? In the next step, what we're going to do, it makes sense if we look at the node with the smallest label, right, with the shortest path. So here we look at A, and then we update all the nodes that are connected directly to A, which is here B, C, and D, right? So we update those. Okay, if we want to go from A to B, for example, in A, the path that we passed so far is its length is 0, and we want to add another link, which is this link, so we add 10 more to the path, right? So we update the label for B here to 0 plus 10, which will be 10, right? And we do the same for C, so this one's going to be 3, and do the same for D, which is going to be 7, right? So these are the new labels, the updated labels. So in the second row of the table, we put them 10, 3, and 7. E is not directly connected to A, so we don't do anything for that. And A is now permanent, so we're not going to touch that until the end of the algorithm. Okay, and in the path table, we are going from A to 3 different nodes, so we have A under B, C, and D. Okay, and then in the next iteration, we do exactly the same thing. So you see for A, the smallest number, we see in the previous iteration that the smallest number is 3, so we make 3 permanent, and we see the connected nodes to C, which are B, D, and E, and then we update them in the same way. So for example, if we want to go to B from C, so far we passed 3, and then we add another link, which is 5. So the new number here for the new label for B is going to be 3 plus 5, which will be 8, and we put it here. And the same thing for E, but there is one thing. Here for D, if you want to go from C to D, the new number would be 3 plus 9, which is 11, which is more than 7, right? So it's not going to be a good pass to reach D. So we don't change the label for D in this stage. So we put it as it is, okay? And the same way we update the pass from C to 2 different nodes here, because we haven't changed D, right? And in the next step, we make E permanent because it has the smallest label, and we do the same thing. And in the next step, we make B permanent because it has the smallest label so far from the ones that are not permanent yet, which is B and D. It has the smallest number, right? So we make that permanent. We have B here, but B is not directly connected to any other node that is not permanent yet, which is D. So B is not directly connected to D. So we don't do anything here. We do not update any label here, right? So we just put B here. And the same for D. The last node that is remained is D. We make that permanent, and all the other nodes are permanent, so we just put D here, and that's it. Okay, so far we have done with the iterations. What is remained is that we should go with the final row. What we do for final row, actually we put the final labels that we found for each of the nodes here. These are the final labels. And also we put the final node that is connected to the initial node here. So it's going to be E, A, and C. Okay? Now from these two tables, we can find the shortest path from each of from A to each of the other nodes. Here's how. Okay, so first of all, what you do is that you draw all the nodes, but without any link, okay? Then you go to the second table, you look at the table here, and you draw the paths that you found here. So for example, here we found that E should be connected to B. So we draw a link from E to B, and from the original network we know that the weight is 2, so we just put 2 here. And the other link is from A to C. Okay, so we draw this. From A to D, we draw this. And from C to E, we draw this. Okay, and we put the labels, the final labels on each of those. So this is the graph, the reduced graph that shows you the shortest path to every other node from A. So for example, if you want to reach B, the shortest path from A to B is going to be this one, right? So it's going to be A, C, E, B. And in this graph, actually, there is only one unique way to reach from A to B, or from A to any other node. So here you have for B, A, C, E, D, and its length is 6, right? And the same thing for the others. From A to E, for example, is A, C, E, and the length is 4. And that's it. With this algorithm, you found the shortest path to all the nodes from an origin at the same time, okay? And now it's your turn to think about what is the order of this algorithm? Is it an efficient algorithm? And the other question is, why do we need the shortest path at all? So what is the application of the shortest path, especially in our course context? How do you use the shortest path in our context? And also, if you do some research, you will find that there are other algorithms like Bellman-Ford, Floyd-Warshall for solving the shortest path problem. So do some research to find what is the difference between these algorithms with Dijkstra's algorithm and what is the pros and cons, and when do we use Dijkstra, when do we use the other algorithms. So we're going to talk about that in the beginning of the next lecture. So do some research on that. And what's next? In the next session, we're going to talk about vehicle routing problem. So many programming problems, including transportation routing, communication, supply chain management, can be regarded as special cases of shortest path problem. Okay, so one of the problems that we want to focus on is vehicle routing problem. We want to see how is it different from the shortest path problem, what are the similarities, what are the differences, and how can we formulate that. See you all in the next session.